Edexcel A-Level Maths Mechanics, October 2020, question 5. A small ball is projected with speed u meters per second from a point O at the top of a vertical cliff. The point O is 25 meters vertically above the point N, which is on horizontal ground. The ball is projected at an angle of 45 degrees above the horizontal. The ball hits the ground at a point A, where AN equals 100 meters, as shown in figure 2. The motion of the ball is modelled as that of a particle moving freely under gravity. For part A, we need to use this initial model to show that u is equal to 28. So we're going to resolve horizontally and vertically. I'm going to start horizontally. In this direction, we've got an initial velocity of u cos 45 degrees, going through that angle there. We don't know what t is, but we do know the distance travelled is 100 meters. Now, as the particle is moving freely, there's no deceleration or acceleration in this direction. So we can say that time multiplied by the speed is equal to the distance travelled. So t times by u cos 45 is equal to 100. Cos 45 is root 2 over 2. So ut root 2 over 2 is 100. So t is equal to 200 over u root 2. Rationalising the denominator is equal to 100 root 2 all over u. We're now going to resolve vertically. I'm going to take all of my measurements in the upwards direction. It doesn't really matter as long as you're consistent with this. So upwards, our initial velocity is u sine 45, which again is u root 2 over 2. T is equal to the 100 root 2 over u that we've just worked out. S is minus 25, so we've done velocity upwards. So as it's going downwards 25 meters, we have to use a negative. And acceleration is minus 9.8, again because the acceleration acts downwards. Looking at what we've got there, S, U, A and T, we're going to use the CVAT equation S equals UT plus half AT squared. So substituting all them in, we get this equation here, which we're going to need to do some tidying up with. Looking at the first term on the right, we've got U top and bottom, so they'll cancel out. We've got root 2 times root 2 on the top, which is 2. And a 2 on the bottom, so they'll cancel out. So we end up with minus 25 equals 100 minus, and that half times 9.8 is 4.9, and squaring the bracket gives us 20,000 over u squared. This gives us minus 25 is equal to 100 minus 98,000 over u squared. So 98,000 over u squared is 125. Rearranging, u squared equals 98,000 over 125, which equals 784, hence u is equal to 28 as required. For part B, find the greatest height of the ball above the horizontal ground, NA. As we're looking for a height, let's resolve vertically. I often like to start by listing all the values we know, then helps us to find which formula we need. So we know that the initial velocity is 28 sine 45, which is 14 root 2. We know that the final velocity will be 0 because at the greatest height, this is the point where the ball stops travelling upwards and is about to start going down again. So it's got 0 velocity. Acceleration is minus 9.8, or force due to gravity. And we want to find our displacement, s. So we're going to use the formula v squared equals u squared plus 2as. Putting our values in, we have that 0 equals the square of 14 root 2 minus 2 times 9.8s. So 0 equals 392 minus 19.6s. S equals 392 over 19.6, which is 20. Now I've got to be careful at this point because we want the greatest height of the ball above the ground NA. We've worked out how far up it travels from O. So we just need to take this value, add on the 25 for the cliff, which gives us a height of 45 meters. In a refinement to the model of the motion of the ball from O to A, the effect of air resistance is included. This refined model is used to find a new value of u. So part C, how would this new value of u compare with 28, the value given in part A? So if we've got air resistance in there, it means the ball is going to slow down a lot quicker because we've got an extra force acting against it. So to travel as far as it did, it's going to need to have a faster velocity to start with, so our new value would be larger than 28. For D, we need to state one further refinement of the model that would make the model more realistic. Now, there are quite a few different things you could say here. We could take the size of the ball into account, the shape of the ball, anything like that. One I usually go with, because I find it easier to remember, is to take the spin of the ball into account. If you've enjoyed this video, remember to subscribe to the Doing Maths channel to keep up to date with all the latest releases.